In this video, we're going to look at a phase change graph, or sometimes it's called a heating curve. If I flip my slide to find the heating curve, there she is. It's at the bottom of your page. I'm hoping this graph looks familiar to you. You've probably looked at this in first year chem. This one is for ice or water. As time goes by, we should make note that heat is absorbed. So we're going to plot heat being absorbed versus temperature change. Sometimes in first year chem we would do this lab. It was terribly boring. Where we'd take a sample of ice cubes and we'd put them in a beaker on a hot plate. And as time goes by and heat is absorbed, we just plot the temperature change. Awesome, right? So we'd usually start the sample somewhere below zero. It wasn't necessarily negative 20, but it was below zero. And we're going to call that section A of the graph. And here it's listed as ice, but in general this should always be the solid phase. So for any substance, this phase graph is going to look similar. This bottom section where the temperature is changing, it's obviously increasing, but this would be all temperatures where we're increasing through the solid phase. Now here's the part of this little lab that I didn't like. So the temperature goes up, everybody's having a great time, and then all of a sudden the temperature is stuck at zero for a while. So then kids would come in and say, oh, I think my thermometer's broke, because if I'm still adding heat, why isn't the temperature going up? Why is it stuck at zero for a while? And it's not wrong, it wasn't the thermometer. We're going to call this section B of the graph. At section B, this is your melting point. At the melting point, two phases are present. You should see both solid and liquid. So here they've got this listed as ice and water. Well, more specifically, let's just put this in as liquid and solid. Both phases are present. If you watch an ice cube melt, you're going to see some of the outer particles start to turn into liquid, but then the inner particles may still be solid until the entire sample has melted. And then magically the temperature starts to go up again. Once the entire sample has melted, now we're going to call this section C of the graph. And this should represent all temperatures where the substance is liquid. So the temperature is stuck at zero during the melting phase change, but then once we've completely changed the phase, if I continue to add heat, the temperature should go up. So anywhere between 0 and 100, the water is a liquid. Now if I were to continue adding heat, I would get stuck around 100 degrees for a while again. The temperature is going to stick at 100. Which would be the boiling point. We're calling that section D. Section D is the boiling point. Boiling point. So again, this could be any substance. The bottom plateau always represents the melting point. The top plateau will always represent the boiling point. And again, if you watch a sample of water boil, you'll see the water vapor, you'll see the bubbles of water vapor forming, but you'll also still see some liquid water. So at the boiling point, we're going to put both. We should see some liquid, and we should see some gas or vapor. Once the entire sample boils and turns to a gas, if I somehow had that gas in a closed container and I continued to add heat, then I would be at section, we're going to call it section E of the graph. And then this would represent temperatures where we are all gas. So I'm kind of hoping that a graph like this is somewhat familiar to you. And again, any substance will have a graph that looks like this same general shape. We just might find melting and boiling points at different temperatures. Okay, so now let's figure out what's happening at these sections of the graph. Let's go back. We've got them labeled. So now when they talk about section A, B, C, this kind of makes more sense. We said section A was the solid phase. The temperature is increasing. Temperature measures kinetic energy, average kinetic energy, which is energy of motion, how fast the particles are moving. So all you're doing at this section A is making the particles move faster. But they're still in the same phase. So even in the solid phase, you're starting to make those particles vibrate a little bit. Throughout the liquid phase, if you increase the temperature, those liquid particles are just starting to flow past one another faster. There's more movement. If we wanted to calculate exactly how much energy is being absorbed at this section of the graph, we would use this equation. It is in the AP packet, but it looks a little different. In the AP packet, it's going to look like this. Q equals MC delta T. Yikes. It means the same thing. Q is like heat capacity. This equation is found in the thermal section of this, the AP equation packet. And they'll tell you what all these symbols mean. So Q stands for like heat capacity, total amount of heat energy. M stands for mass. C is specific heat capacity. Nobody ever understands why it's C, but it is. Specific heat. We might want to make a little note if you forgot. It's the amount of heat needed to increase the temperature of 1 gram of whatever substance you have up 1 degree Celsius. Cool. It's a constant. It would be given to you. And then delta T is obviously change in temperature, so this equation actually kind of makes sense. So you look up specific heat. It's a constant. It's defined as the amount of heat in units of joules required to increase the temperature of 1 gram up 1 degree. Well, what if you have more than 1 gram? Then you multiply by the mass you do have. What if you want to change the temperature more than 1 degree? You multiply by your temperature change. Piece of cake, right? This equation is going to be plug and chug. Now you get to section B. And we mentioned it was the melting point. We mentioned that you should see both solid and liquid phase. I mean, think about an ice cube really melting. You will see both phases present. But people really have a hard time understanding why the temperature doesn't increase. And sometimes they'll give an answer, like on an AP test, the question might say, why is there no temperature change? And they'll say, because it's melting. Okay, well, that's not wrong. Yeah, this is the melting point, but why doesn't the temperature change? If we're still adding heat, that's the kicker. It's not like I turned off the hot plate. I'm still adding heat energy. And they always assume then that if you add heat, the temperature should go up. But at a phase change, that heat energy is being used for a different purpose. Think about a solid. The particles in a solid are packed real tightly together. There they are. So let's say this is an ice cube. These are water molecules or something like that. If you want to change phase, you have to add heat energy. But that heat energy is not being used to increase the kinetic energy. It's not just being used to make the particles dance around faster. We want to change phase. In order to change phase, we need to do this. We need to overcome the intermolecular forces. And now, depending on how strong those intermolecular forces are, we may need more or less heat to do this phase change. So if I think about these particles, there's some kind of attractive force between the molecules. That's what I need to break. So let's pretend that right there is an IM force. An intermolecular force. I'm adding energy, but the energy is being used to break intermolecular forces, to overcome intermolecular attractions, not to make the particles just move around faster. That would cause a temperature change, because kinetic energy and temperature measure the same thing. Now again, we'd say that it stays at 0 for quite a while. Well, yeah, I mean, obviously the energy is going to be absorbed by the outer molecules first, so we'll break those intermolecular forces, those outer particles turn into a liquid. But then we go to the next layer and the next layer and so on, and we're going to stay at the melting temperature until all particles have changed phase. So at the beginning we're going to see mostly solid, a little bit of liquid. Toward the end, we should see mostly liquid and just a small amount of solid remaining. Not until the entire sample has changed phase will the temperature increase again. If we wanted to calculate exactly how much energy is needed to melt a substance, we use heat of fusion. Here's our equation for heat of fusion. It's defined as the amount of energy required to melt 1 mole of the substance. Now, sadly, they don't give you this equation in the AP packet, so some people freak out. But it makes sense. If, for example, water, if this were water, delta H FUS for water, heat of fusion, is 6.00 kilojoules per mole. I can squish it in there. And that's, again, a constant value. They would give that to you. That'd be given. It takes 6 kilojoules to melt 1 mole of ice. What if you have 2 moles of ice? You multiply by the moles that you do have. So that's why they don't really give you this equation, because you can figure this out. If you have more or less than a mole, you just multiply by the amount of moles that you do have. And again, the heat of fusion value is a constant. That would be given to you. Okay, so now we follow the same trend through the other sections of the graph. Section C is the liquid phase. And so again, now when I see the temperature change, I should see an increase in kinetic energy. Oh, I was doing this in blue. Yeah, that's perfect. If I increase temperature, I should see an increase in kinetic energy. The particles are just moving faster. And now since there is a temperature change again, I can go back to this equation. Mass times temperature change times specific heat, or in the AP packet, mass times specific heat times temperature. Same gig, right? You can use this equation whenever there is a temperature change, which then obviously at section B, the melting point, there is no temperature change, so you can't use this equation. You have to use moles times heat of fusion. A common question they might ask us at some point, they might say, hey, what's the difference? I have water at 60 degrees Celsius versus water at 80 degrees Celsius. They might say, hey, what's the same, what's different? And we'd say, okay, well, I'm pretty familiar with water. I know that anywhere between 0 and 100, water should be the liquid phase. So they're both liquid. Then if they ask, well, what's different? What's different between particles at 60 degrees versus 80 degrees? I would just say, well, at 80 degrees, the particles have more kinetic energy. At 80 degrees Celsius, particles have more kinetic energy. Or you could say they move faster. The particles have more movement. They're still liquid, they're just dancing around a little bit faster. Oh, I kind of remember that. Okay, so now we got our graph. The last two sections are D and E, which again are really similar to what we kind of previously mentioned. D is the boiling point. There is no temperature change at a phase change because again the energy being added is used to overcome intermolecular forces. We're trying to separate those particles from the liquid phase into the gas phase. We'll see both phases present because the temperature will stay at the boiling point until the entire sample changes phase. So I'm going to see at the beginning lots of water, maybe a few bubbles. Toward the end, I'll see like rapid bubbles. I'll probably see the steam. and then there might be a small amount of liquid water left. So energy is still being added, even though the temperature is not changing. The energy added is just used for a different purpose. Instead of increasing the temperature and the kinetic energy, we're changing phase. And in order to change phase, we have to increase the energy level to overcome intermolecular forces. If you wanted to calculate this amount of energy, you would use a really similar equation. It's moles times heat of vaporization. And so again, heat of vaporization would be a constant. They would give that to you. It's defined as the amount of energy needed to boil or vaporize 1 mole of a substance. And then we just multiply by the amount of moles that we do have. Finally, as I get to section E, the gas phase, again, all particles are gas. We've changed phase completely. So now if I keep adding heat energy, I'll just make the particles move faster. I'll increase the kinetic energy. And again, that's why the temperature increases. Temperature measures average kinetic energy, average movement of the particles. And since I have a temperature change, I can go back to this guy. Mass times temperature change times specific heat.